All right, welcome back. Back by popular demand. I'm gonna keep reading the AI engineering book. I had no plans to stop reading it, but this is the first. So this '04 update is the first time I've ever actually had a real coding experience where it's like, oh, I can actually make something useful. So like I can make a metronome that not only has all the features that have been missing in Eskimo, but Metronome, but it taught me how to actually host it using GitHub Pages. So this is hosted up there live on the internet for anyone to use. So like that's exciting. Like I know like any idiot could have like hosted it up on GitHub Pages or y- except me. Like I didn't know that feature existed, and this is the first time the AI was smart enough to be like, oh well, you can just put it on GitHub Pages. You don't have to pay for anything. What you're paying for when you have your own site is you get your custom URL, and then you pay for a platform that can do more sophisticated things than just host up a static page like this. So, but in the meantime, as I'm developing this and stuff, like this is totally fine. So that's a big part of the moving away from this series is just the AI is getting so good now that like um, I just wanted to play with the AI. But anyways, this is going to be the start of chapter six. I've got about 20 minutes here at least. So this is on reg and agents. To solve a task, a model needs both the instructions on how to do it and the necessary information to do so. Just like how a human is more likely to give a wrong answer when lacking information, AI models are more likely to make mistakes and hallucinate when they are missing context. For a particular application, the model's instructions are common to all queries, whereas context is specific to each query. The last chapter discussed how to write good instructions to the model. And we remember there was kind of a you have to give it a role, you should give it a context, you should give it a so like it's much better just, rather than say, hey, I'm doing I'm trying to write a paper on on this topic. Can you grade the paper? That's not as good of a prompt as act as an English teacher that specializes in this topic. Uh, uh, Provide this is my final paper that's like that helps that sort of thing. So this chapter focuses on how to construct the relevant context for each query. Two dominating patterns for context construction are RAG, or Retrieval Augmented Generation, and agents. The RAG pattern allows the model to retrieve relevant information from external data sources. The agentic pattern allows the model to use tools such as web search and news APIs to gather information. And I want to take a quick pause here as well because I just recently installed a new extension. I think I might have. Yeah, so I think it came from some Reddit post I saw or something like that. But the name of the extension is Bring Your AI. So so we can click. So for some reason it's not installed. Um, but what you can do is yeah, so it's an extension on VS Code, and it's also a browser extension. So so we have to log into something. I'm not sure what. Open that. We'll log into WHOP, whatever that is. So I'll willy-nilly log in and give away all my personal information, as one does in today's society. Um, okay, so it's a powerful combination of a VS Code extension and a web extension designed to seamlessly integrate into your code-based context from VS Code directly into any AI chat website. So basically, what you can do is use RAG, retrieval augmented generation, but it retrieves your own code that you wrote in VS Code. So you can have it set up to use. Yeah. So let's yep. So let's open that. There we go. So now it's got a port open. Oh, I don't have it. Oh, do I need a subscription? Pay. Everything in the world you have to pay for. Yeah, shit. Well, I have to pay for it. Okay, well, never mind. I didn't realize I had to pay for it, which is on me because you have to pay for everything. So I'm already paying too much for OpenAI, so I can't pay for everything in the world. Uh, okay, you don't have a. Yeah, I have to. Yeah, I have to get access for. Okay, well, never mind. I'll deal with that later. Uninstalling it later. But so if you want, you can pay for a tool like that and connect it up to your to like VS Studio Code, which would be awesome. While the reg pattern is chiefly used for constructing context, the agentic pattern can do much more than that. External tools can help models address their shortcomings and expand their capabilities. Most importantly, they give models the ability to directly interact with the world, enabling to automate many aspects of our lives. Both RAG and agentic patterns are exciting because of the capabilities they bring to already powerful models in a short amount of time. They've managed to capture the collective imagination, leading to incredible demos and products that convince many people that they are the future. This chapter will go into detail about each of these patterns, how they work, and what makes them so promising. RAG. RAG is a technique that enhances the model's generation uh, by retrieving relevant information from external memory sources. An external memory source can be an internal database, a user's previous chat sessions, or the internet. The retrieve then generate pattern was first introduced in reading Wikipedia to answer open domain questions, Chen et al., 2017. In this work, the system first retrieves 5 Wikipedia pages most relevant to a question, then a model. Um, then a model uses or reads the information from these pages to generate an answer as visualized in Figure 6-1. So, question: how many of Warsaw's inhabitants spoke Polish in 1933? That's interesting. I would guess somewhere near the population of Warsaw. All right, so then it retrieves the relevant documents, which I can't really read there. Um, and then it's yeah. So 6-1 retrieve then generate pattern. The model was referred to as the document reader. Oops, how do I? I'm not able to go back a page. Oh, okay. So this is page 413. So let's go to the next page, 414. Oh, we went to 415 rather than 414. Uh, Shoot. I'm in VR, so it's hard for me to change the pages. Oh, there we go. I can use my keyboard. Oh, okay. So we are going to go from 413 to. Okay, because we're showing 2 pages at a time. The term retrieval augmented generation was coined in retrieval augmented generation for knowledge intensive NLP tasks, Lewis et al. 2020. The paper proposed REG as a solution for knowledge intensive tasks where all the available knowledge can't be output into the model directly. With RAG, only the information most relevant to the query, as determined by the retriever, is retrieved and input into the model. Lewis et al. Found that having access to relevant information can help the model generate more detailed responses while reducing hallucinations. For example, given the query, can Acme's fancy printer A3 100, print 100 pages per second, the model will be able to respond better if it's given the specifications of fancy printer A3000. So yeah, really good thing you can do is in your prompt upload the manuals. So find the manuals to things, download them, and then upload them as a file. That's a good thing to do. You can think of RAG as a technique to construct context specific to each query instead of using the same context for all queries. This helps with managing user data as it allows you to include data specific to a user only in queries related to this user. Context construction for foundation models is equivalent to feature engineering for classical ML models. They serve the same purpose, giving the model the necessary information to process an input. In the early days of foundation models, RAG emerged as one of the most common patterns. Its main purpose was to overcome the model's context limitations. Many people think that a sufficiently long context will be the end of RAG. I don't think so. First, no matter how long a model's context length is, there will be applications that require context longer than that for sure, especially once we're getting into science stuff. To create the image of the black hole, um, you know, that sort of thing, they needed like they'll no matter how long the context is to analyze the universe, you're going to need a longer context than that. After all, the amount of available data only grows over time. That too. People generate and add new data, but rarely delete data. Context length is expanding quickly, but not fast enough for the data needs of arbitrary applications. Second, a model that can possess long context doesn't necessarily use that context well, as discussed in context length and context efficiency. The longer the context, the more likely the model is to focus on the wrong part of the context. Every extra context token incurs extra cost and has the potential to add extra latency. RAG allows a model to use only the most relevant information for each query, reducing the number of input tokens while potentially increasing the model's performance. Efforts to expand context length are happening in parallel with efforts to make models use context more effectively. I wouldn't be surprised if a model provider incorporates a retrieval like or attention like mechanism to help a model pick out the most salient parts of a context to use. Note, Anthropic suggested that for Claude models, if your knowledge base is smaller than 200,000 tokens, about 500 pages of material, you can just include the entire knowledge base in the prompt that you give the model, with no need for RAG or similar methods. It'd be amazing if other model developers provide similar guidance for RAG versus long context for their models. And there is something called catastrophic forgetting. So even if you have a large context window, um, the, the phenomena. So what can happen is the the beginnings and the ends of the context window are remembered better than the middle. So you could feed it, you know, 1,000 books, and it could, you know, the 500th through the 600th books just completely don't even register because of the flaw of catastrophic forgetting in a context window. And because of that, you ask it like you're, let's say you feed it all of Shakespeare's plays, and then you ask it questions about the plays. You feed it in chronological order. You add a question about the plays in the middle of Shakespeare's career, and now it hallucinates or gives you bad answers. You know, it knows about like Louis the Third or what, but you know, it doesn't know about um, uh, prequels or sequels in the correct way. So Anyway, RAG architecture. RAG system has two components. A retriever that retrieves information from external memory sources, and a generator that generates a response based on the retrieved information. Figure 6-2 shows a high-level architecture of a RAG system. So external memory, documents, tables, chat history, etc. Retriever, context relevant to query, generative model, figure 6-2, a basic RAG architecture. Okay, so when you prompt, um, uh, yeah, so the retriever can pull down external memory, and it can do that as much as it needs to enhance the response. In the original RAG paper, Lewis et al. Trained the retriever and the generative model together. In today's RAG systems, these two components are often trained separately, and many teams build their RAG systems using off-the-shelf retrievers and models. However, fine-tuning the whole RAG system end-to-end can improve its performance significantly. The success of a RAG system depends on the quality of its retriever. A retriever has two main functions, indexing and querying. Indexing involves processing data so that it can be quickly retrieved later. Sending a query to retrieve data relevant to it is called querying. How to index data depends on how you want to retrieve it later on. Now that we've covered the primary components, let's consider an example of how a RAG system works. For simplicity, let's assume that the external memory is a database of documents, such as a company's memos, contracts, and meeting notes. A document can be 10 tokens to 1 million tokens. Natively retrieving whole documents can cause your context to be arbitrarily long. To avoid this, you can split each document into more manageable chunks. Chunking strategies will be discussed later in this chapter. For now, let's assume that all documents have been split into workable chunks. For each query, our goal is to retrieve the data chunks most relevant to this query. Minor post-processing is often needed to join the retrieved data chunks with the user prompt to generate the final prompt. This final prompt is then fed into the generative model. Note, in this chapter I use the term document to refer to both document and chunk because technically a chunk of a document is also a document. I do this to keep this book's terminologies consistent with classical NLP and information retrieval (IR) terminologies. Retrieval algorithms. Retrieval isn't unique to RAG. Information retrieval is a century-old idea. It's the backbone of search engines, recommender systems, log analytics, etc. Many retrieval algorithms developed for traditional retrieval systems can also be used for RAG. For example, information retrieval is a fertile research area with a large supporting industry that can hardly be sufficiently covered within a few pages. Accordingly, this section will cover only the broad strokes. See this book's GitHub repository for more in-depth resources on information retrieval. Note, retrieval is typically limited to one database or system, whereas search involves retrieval across various systems. This chapter uses retrieval and search interchangeably. All right, so that's important to note because they're talking about either something that could be limited to one database or system, or retrieval across various systems. And what makes it even more confusing is retrieval is the one that talks about one database or system, and search is the one that involves retrieval across various systems. All right, so at its core, retrieval works by ranking documents based on their relevance to a given query. Retrieval algorithms differ based on how relevance scores are computed. I'll start with two common retrieval mechanisms, term-based retrieval and embedding-based retrieval. Sparse versus dense retrieval. In the literature, you might encounter the division of retrieval algorithms into the following categories: sparse versus dense. This book, however, opted for term-based versus embedding-based categorization. Sparse retrievers represent data using sparse vectors. A sparse vector is a vector where the majority of the values are zero. Term-based retrieval is considered sparse, as each term can be represented using a sparse one-hot vector, a vector that is zero everywhere except one value of 1. The vector size is the length of the vocabulary. The value of 1 is the index corresponding to the index of the term in the vocabulary. If we have a simple dictionary, so here's a dictionary, looks like oh yeah, so this is, it could be a, so this is a, yeah, like a Python dictionary. So here's the value, it's a string food, FOOD, uh, colon 0, banana 1, slug 2. Then the one hot vectors of food, banana and slug, are 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1 respectively. So these are the different ways. Wait, what? I am not. This is not registering with me because, yeah, this is not registering with me. Okay, not at all. Yeah, that's not registering with me. Let's get help from the AI. Okay, so I'm just gonna take a screenshot of this, dump it into the AI. All right, and then let's get a screenshot of the next page. All right, dump that into the AI. All right, and then we'll just have that dumped in without any without throwing anything, and then we'll start a conversation with it. All right, and I'll keep reading as that's going. Dense retrievers represent data using dense vectors. A dense vector is a vector where the majority of the values aren't zero. Embedding-based retrieval is typically considered dense, as embeddings are generally dense vectors. However, there are also sparse embeddings. For example, SPLADE, SPLADE, sparse lexical and expansion. Where's the D? Okay. Is a re retrieval mechanism that works using sparse embeddings. It leverages embeddings generated by BERT, but uses regularization to push most embedding values to zero. The sparsity makes embedding operations more efficient. The sparse versus dense division causes SPLADE to be grouped together with term-based algorithms, even though SPLADE's operation strengths and weaknesses are much more similar to those of dense embedding retrieval than those of term-based retrieval. Term-based retrieval versus embedding-based division avoids this miscategorization. All right, so the next is term-based retrieval. Uh, I am at the 4 p.m. mark. The 4 p.m. mark is I don't have a ton of time. I have to meet an obligation, so the 4 p.m. mark is the mark where I'm running out of time to get ready. In fact, I gotta hit the road. Yeah, all I have time for is really a shower and to gather up my stuff. So I'm gonna have to stop here at term-based retrieval. Let's try to have a brief 5 minute conversation here. All right, so specifically what I want to discuss with you here regarding those screenshots is so I didn't understand the example. So they gave a simple dictionary, presumably a Python dictionary, with the keys food, banana, and slug, but then the values were 0, 1, and 2. So I don't understand how that creates a one hot vector of food, banana, and slug that are 100, 010, and 001 respectively. Because what happened to the value 2? Like, why did that get changed to 0?
Got it. Let me break it down for you. When they mention the dictionary with food 0, banana 1, slug 2, they're essentially assigning a unique index to each term in the vocabulary. Food corresponds to index 0, banana corresponds to index 1, slug corresponds to index 2. A one-hot vector is a vector where only one position is 1, indicating the presence of that term, and all other positions are 0. The length of the vector is equal to the size of the vocabulary, in this case. So, food is at index 0, so its one-hot vector is 1, 0, 0. Banana is at index 1, slug is at index 2, so its one-hot vector is 0, 0, 1. The values 0, 1, 2 in the dictionary aren't used as actual values in the vector, they're just the positional indexes. The one-hot vector simply sets the corresponding index to 1 and everything else to 0. So the value 2 doesn't get changed to 0, it's just indicating the position where the 1 will be placed for the slug term. Does that make sense?
I mean, if assuming this is Python, it would make sense if it were like a a list, and I think you can even make a list in Python of like a key value list rather than a dictionary, using some like imported thing from like collections or whatever. I forget what that's called, but it doesn't make sense to me because I thought that the order of a dictionary in Python doesn't persist. So like I don't understand how like the one hot vector for food being 100 would be actually representative of where food is in the dictionary, because I thought like like Python dictionaries didn't have they're not the same as lists where like the first entry is always the first index.
I see what you're getting at. Let's clear that up. Historically, Python dictionaries weren't guaranteed to maintain insertion order, but since Python 3.7, dictionaries do maintain the order of insertion. However, that's not really the core point here. In the example, the dictionary food 0, banana 1, slug 2 isn't about the dictionary's internal ordering, it's about assigning a fixed index to each term in a vocabulary. In other words, the dictionary is just a convenient way to map each term to a unique, consistent integer index. The resulting one-hot vectors are based on these indices. So it's not the order of the dictionary that matters, it's that food is assigned index 0, banana index 1, and slug index 2. The one-hot vectors use these indices to place a 1 in the position corresponding to the term's index and 0 everywhere else. Think of it as a predefined mapping of terms to indices that allows the model to create a consistent and reproducible vector representation. This indexing is essential for creating one-hot vectors in a vocabulary of fixed size. Does that help clarify things?
Yeah, I think so because the goal here is retrieval, right? So you're basically like you're basically like saying you're like labeling the bins it belongs to, right? It's like if you have in your room three bins, one where you store toys, one where you store clothes, and one where you store books. You can write you can say we say, go get me something out of the first bin. Go get me something out of the second bin, out of the third bin. So you can have a one hot vector that basically serves as that. You go get me something out of bin 100, bin 010, and you can have it be completely unambiguous that way, which bin is which, as they start to become more more complex than it would be for a human to like practically understand.
Exactly, you've got it. The one-hot vector acts like a label indicating which bin or category the item belongs to. Each position in the vector corresponds to a specific bin or term, and a 1 in that position indicates the presence of that term. This way, you get a clear, unambiguous representation that can be easily processed by algorithms. As the vocabulary grows, each term still gets a unique position, making it scalable and straightforward for retrieval tasks. So just like labeling and retrieving items from bins in a room, the one-hot vectors make it clear which term is being referred to, even as the number of terms increases. When
All right, and that's all I've got time for. So thanks for watching, and see you in the next one.